Hi students, good morning. In the last class we discussed about applications of Gauss Law, like some calculations based on the flux calculations when some charge distributions were given. So in all those problems just we need to calculate some Q inside. So if you are able to calculate the Q inside, you can find the flux passing through that. So let us continue some more examples based on that, some more problems based on that. So in that I am taking a case like, let's say a circular ring, let us consider. Means this is a circular, that means this one is imaginary sphere. Through the center of the imaginary sphere of radius, or an imaginary ring is passing here. So let's suppose the center of this circle will be here. So this is a ring of having this linear charge density lambda here on this. Or let us take a charge Q is distributed totally on this. So write that as a problem. A charge Q is distributed uniformly. A charge Q is distributed uniformly on a circular ring of radius r. On a circular ring of radius r. This ring is assumed to be passing through. This ring is assumed to be passing through the center of an imaginary sphere. Center of an imaginary sphere of same radius r, as shown in figure. As shown in the figure. Then what is the flux passing through the imaginary sphere? Then what is the flux passing through the imaginary sphere? That means both the radius are same only. So then center of this, this is the center of the sphere, let us consider. This is the sphere we are taking, and this is a ring. And so now this circular ring is passing through the center of the sphere. Then automatically the center of the ring should lie on the surface of this sphere, right? Because both are having that same radius. And so just we need to calculate the flux passing through this imaginary sphere. And we solved so many problems, like in order to calculate the flux passing through that imaginary sphere, so we need to take just what is the charge enclosed by this. So that means from here to here, clearly that is the charge present inside this. So this, how much charge is present inside this hemisphere, we need to calculate here. So that is the thing we need to do here. And so for that you can use any concepts here, like whatever you know by seeing the diagram. So just I am taking like this. This radius will be r. From center of the sphere to the surface of the sphere I am taking, or you may consider from center of the ring to the surface. This C1 is the center of the sphere and C2 is the center of this ring. From the center of the ring, I am drawing this another line to the surface of the ring until this point here, right? Then you can say that should also be radius r only, right? Next, from the center of this sphere, I am drawing a line to its surface. So this is also radius r only, right? So that means now this is radius r, this is radius r from center of the sphere to the surface of the sphere, and this is from the center of the ring to the surface of the ring, so this is also r. So that means this is an equilateral triangle, so that you can write this angle as 60 degrees, right? Similarly, let us form another triangle below this. So that means just similar to that we can draw one line here and another line here. So this is also r and this is also r. So that this angle is also 60 degrees. And so that now if you are taking this as a arc here, this is circular arc. At the center of the circle, this circular arc is subtend an angle of 120, 60 plus 60. And so that we can write that as charge enclosed will be equal to Q by 120 degrees, means we can write that as 1/3, because total it is 360 degrees. The charge q is distributed in an angle of total 360 degrees. So it is 1/3. Or in terms of charge per unit length, you can write here. That means in terms of charge per unit length, you can write this as lambda is equal to, I can write this as q by 2 pi r, we can write. That is lambda value. Then this charge enclosed we can write as q by 2 pi r into length of that arc we need to write. Length of that arc we can write as 2 pi by 3 into r, because r theta formula. This total angle is 120 degrees. So 120 degrees means I can write as 2 pi by 3 into r. That gives the length of this arc. So charge per unit length into length of this part, or directly you can write that as total 360 degrees. So 120 degrees means it is 1/3. So 1/3 of the charge will remains inside. Therefore this will be q by 3, you can write here. And therefore flux passing through that surface we can write as 1 by epsilon naught times q in, and therefore it is q by 3 epsilon naught we can write. So it is a flux passing through that. So such a simple type of questions will be there. Just you need to calculate that by using the given information. You need to calculate that what is the charge enclosed by the surface. If you are able to calculate the charge enclosed by the surface, then you can calculate automatically this flux passing through the given surface. Like suppose sometimes they will give the situations like this. This is a cone, for example, let us consider here cone of this base radius r and say height h. Now it is placed in uniform electric field of intensity E here. This cone is placed in a uniform electric field of intensity. Then what is the flux passing through that cone? That means flux entering that cone you may consider. What is the flux entering that cone? So write that as the next question. A cone of height h and a base radius r is placed in uniform electric field of intensity E. Is placed in uniform electric field of intensity E. As shown in the two cases. Then what is the flux passing through the flux entering the cone? Then what is the flux entering the cone? In both the cases. So that means in one case the cone is placed like vertically, now it is placed like this, so that the flux is entering through the base of this cone here. And so now here, for example, if I consider this case here, the flux entering the cone is nothing but I can take the projection of this cone in 2-dimensional. Then whatever the area is there, then whatever the area, that 2-dimensional area you are getting, then flux passing through that area will be the flux entering this cone we can consider here. That means the 2-dimensional projection of this cone is nothing but I can consider it as, in case 1, the 2-dimensional projection is nothing but a cone like this, that means triangular like this. This is a triangle of height h and a base 2r. That means this area we need to consider perpendicular to this electric field here. If electric field lines are like this, then the triangle will be like this. Triangular will lying in this plane here. Then electric field will be like this. Then whatever the area of the triangle is there, through that area this electric flux is entering here. So that we can consider like this, that we call projection of this given diagram. So whatever the 3-dimensional diagram is given, such a projection we need to consider there. And the projection concept we use it in fluid mechanics. Do you remember that? We used that projection concept in fluid mechanics when you are calculating the horizontal component of force due to the static fluid. And so now similarly we are using such a concept here. And so now the area of this projection we can write as this is a projection of the cone. So projection of cone we are considering like this, and therefore this flux we can write as flux entering the cone we can write as phi is equal to E into A we can write. That means cos 0 we can consider here, just we are considering like that. And so that flux passing through this triangular surface we need to write here E into, I can write this as area as 1 by 2 into 2R into 2R into H. And so that this flux is, you can write this as E into R into H you can write here. So it is a flux passing through that cone. And whereas similarly if you are taking this example, this case if you consider here. So similarly let us take the projection. Projection of that cone will be projection of cone in second case. So simply you can consider that whatever the flux entering this base of the cone, that flux only will pass through that cone here. And so that we can write as, that means area of that flux we can write it as E into A. So then E into that area of the cone we can write as pi r square. Just here you will get projection of the cone as like this. It means you will get this as a circular disc here. Circular disc of radius r. Then E into pi r square. You may place the cone in reverse order. That means you may place the cone like this. In the electric field, for example, if the cone is placed like this, in this case also the flux will be same only. Even if the cone is placed like this, in that case also the flux we can write as E into pi r square. That means the projection of that will be, again you will get the base of the cone only, the disc at the base of the cone only you will get. So in that case also you can write this as E into pi r square. There is a flux entering that cone here. That means just we are taking that what is the flux passing in the sense here, what is the entering that cube we are calculating here. So there is a flux passing through that. We need to take just a projection of that. So if your cone is placed like this, then we can write flux passing through that cone we can write as E into R into H. If it is placed like this, we can write it as E into pi r square we can write here. And such a lot of questions will be there. Just we need to take such a projections there in such a cases. Like sometimes they will give like a curved surface they will give here, and here they will give some, this is a circle of radius r. And this may be any surface. It may be hemispherical surface, or it may be any paraboloid surface, whatever may be the surface. Or instead of this hemispherical surface, I am taking some paraboloid surface like this. So even then its base is a circle, for example I am taking here. Even if it is placed in an electric field like this, uniform electric field of intensity E. So then flux passing through that we can write it as E into pi r square we need to write here. So that is a flux passing through that cone here. So in, for example, particularly they will asking about what is the flux passing through the plane surface and what is the flux passing through the curved surface. Then you need to write the proper sign also. In the previous case or this case, I am not considering about the sign. Just we are calculating the magnitude there. If particularly if they are asking what is the flux passing to the curved surface in this case, and what is the flux passing to this cone surface if they ask for example, then we need to use our previous problems. In the just after the completion of the Gauss Law statement, we solved some problems there. The total flux is nothing but we need to write like flux through the plane surface plus flux through the curved surface. So in this case also it is placed in uniform electric field, so it will be 0. So that concept we need to use here. If they are asking particularly about flux passing through the curved surface or flux passing through the plane surface. Otherwise if just they are asking the flux passing through the given surface, then we can directly write its magnitude like this, right? So for example in this case if I consider, then flux passing through the plane surface will be minus you will get, because area vector will be this side and electric field is this side, then minus E into pi r square you will get. Then flux passing through the curved surface will be plus of E into pi r square you will get, because their sum should be equal to 0, because no charge is enclosed by this curved surface here. So like that we need to answer that according to that given question, whether they are asking through the curved surface particularly or through the plane surface particularly, or just they are asking flux passing through the given surface. So accordingly we need to answer those questions there. So this is a projection method. And here sometimes one more method is required to calculate the flux, that is by constructing a complete diagram. By constructing a complete diagram is that model also actually we discussed it already, like if you are taking this hemispherical surface. So at the center of this hemispherical surface if you are placing a charge. So in this we already discussed that we need to take that charge belongs to that hemisphere as q by 2, right? So why we are taking that as q by 2 means we imagine a complete sphere here. So we imagine a complete sphere, so that flux passing through the sphere will be equal to q by epsilon naught we can write. As this charge is symmetrical for both the hemispheres, so flux passing through the hemisphere we are writing as q by 2 epsilon naught, right? So that is why we are taking the charge belongs to that hemisphere as q by 2 we are taking there. So such a similar problem is there. So let us see this. That means we are constructing a complete diagram here when only a part of diagram is given for us. So we need to imagine a complete diagram. From that you can do the calculation, flux calculations easily. Suppose now here a point charge is placed like this. Now this is a plane of square. This is a square plane A of side A. Now a charge Q is placed here. A point charge Q is placed above the center at a distance of A by 2. Got it? Now we need to write the flux passing through the plane of that sphere. So write that as the next problem. A point charge Q is placed above the center of a square at a distance a by 2 from the center, where A is the side of this square. Then find flux passing through the sphere. So if you want to calculate this flux calculation by integral of E bar dot dA bar, because electric field is changing. For example, if I take an element here, the electric field is changing as well as angle is also changing here. So it's a lengthy calculation if you are using that integration method, integral of E bar dot dr bar. So instead of that we use a Gauss law, and in that Gauss law also we are going to use a construction method, that means to take the complete diagram. So this is a part of diagram is given for us, a square in the sense. So if you are making it as a complete diagram, then such that the given charge will becomes a point inside the given diagram, and then you can write the flux passing through that total object we can write. From that the given part we can calculate here. So just by observing that, let us identify that how to cancel that problem now, how to take it as a complete diagram. So just it is given that it's a square, and for that square its side is A, and we are placing a charge above the center here. Now what I am going to do is, I am constructing a complete cube with the side A. So if I am completing a cube here, for example, so this is a cube I am going to construct here. Got it? Now that becomes a cube. And so now for that cube, as a side this distance is A, now the side of this cube will be A, and our charge is placed at the center of the cube. Therefore we can write that as flux through the cube is equal to, this is the net flux, q by epsilon naught we can write, because now the charge q is completely enclosed by that hemisphere, that cube. Now flux passing through the each phase. So flux passing through each phase is nothing but, that is nothing but our flux passing through the given square here. That is our required value. So as the charge is present at the center, so we can write it as 1 by 6 times that of the net flux, right? Because that charge, that flux will be symmetrically distributed among all the 6 phases there. Therefore, I can write this as flux passing through that given square, we can write it as q by 6 epsilon naught. See here how simple this problem is if you are taking such a construction method, if you are constructing the complete diagram. If you are using a integration method for this, it's a very lengthy method, very lengthy calculation you will get here for this, particularly for this square problem. So that means if you are using such a construction method, when only that such a plane surfaces or such a half of the diagrams are given for us, so we need to construct the complete diagram so that you will get the flux calculations will be easy for us. So all this is one type of calculations here. And next here, in some calculations, in some problems, we need to use that solid angle. If you are using the solid angle concept, we can solve some problems easily. So just I will explain the definition of the solid angle, and from that we will solve some problems there now. So I think you know all of you that solid angle definition in the first topic generally we will define that basic definition of the solid angle. So solid angle. So plane angle, all of you know, we define in a plane the angle made by the circular arc at its center we can define, that is length of the arc by radius we can define there. That's a plane angle. And its unit is we know radian. Now the generalization of that plane angle in 3-dimensional is nothing but we call solid angle. That means this solid angle is defined in 3-dimensional. It is a generalization of that plane angle in 3D. So plane angle is defined only for a plane, that means in 2-dimensional. Now this solid angle means we define in 3-dimensional here. So like if suppose if I am taking a small part of a hemisphere, small part of a spherical surface, like suppose this is a complete sphere here, or let us take a complete sphere. So in that complete sphere I am taking a small part like this, a dA. Now angle subtended by that small element at its center, small area element. Now that's area, it's not arc, it is an area at its center. So that this angle, a 3-dimensional angle, so that angle is nothing but we called solid angle. We represent with that d omega, or we may write solid angle means we represent like this omega, and this is all let us consider. And so now mathematically it is defined as now. So mathematically the solid angle is defined as, so solid angle this d omega is equal to dA by area of that element by square of the radius. Like plane angle we are defining as length of the arc by radius we are defining, right? And so now the solid angle is defined as area, the ratio of area of the element to square of that radius. And so now its unit will be steradian. So it is a unit of this solid angle. So just write the definition. Solid angle is defined in 3-dimensional, is in 3D. It is defined as the ratio of, area of the small element to the ratio of area of the small element to square of the radius. square of the radius. Square of the radius of the sphere of which this element is a part. Square of the radius you can leave, but clearly radius means it is not the radius of the element. It is the radius of the sphere of which this element is a part. So that radius we are taking there. So it's a radius of the element of which, radius of the sphere of which this element is a part. So that is d omega is equal to dA by r square. So then its unit will be steradian. It's a dimensionless quantity. You know the plane angle and solid angle are dimensionless quantities. And so just we are the unit we are giving here, the SI unit will be steradian. And so if there are certain cases like if that area is not perpendicular to this radius here, like for example, I am taking like if the area is like this, if the dA is like this, then you can define that angle as this d omega as according to this we can define here, right? dA by r square we can write. If suppose that area is not like that, now let us see here, instead of this I am taking this area element like this. This area I am taking like this, such that it is not normal to this, it makes certain angle here. This is a normal here there. Now this dA is making certain angle theta here. That means we are taking area element as like this. Small area element we are taking like this, which makes an angle theta with this normal here, right? So in that case just we need to take the projection of that. So projection of that means you will get a now perpendicular area you will get here, this element you will get here. So now that element you can take that as dA cos theta you will get here, because here this angle you will get theta, and so that element will be dA cos theta. So that means in that case the solid angle we can define it as, so solid angle we can define it as d omega is equal to dA cos theta by r square we need to write here. This distance we consider as r. So that means when that area is making certain angle theta with the normal, then we need to take that component of that dA cos theta, normal component we need to define there. Then in such a case we define that solid angle as dA cos theta by r square. This much don't confuse with that, much information is not required, just we derive one relation between solid angle and the plane angle of the in case of a cone, semi-vertex of angle of the cone, and only that relation is required for us. Now if you are taking for any complete object, for complete three-dimensional object if you are taking, then the solid angle we need to write here. For example, let us take in case of a sphere itself. So let us write this is just a definition for this small elements here. So the solid angle of a complete sphere, solid angle of a complete sphere, so that I can write that as integral of d omega, simply that omega is equal to, so which I can write as integral of dA by r square, right? So in case of a sphere like previous our cos theta term, that value will be 0 you will get, because this area will be normal only. If you draw a line from the center, it will be normal to that only, so that theta value will be 0 there. And so now here this value I can write as 1 by r square. For example, I am taking this as a sphere now. So for sphere, so that r is a constant value, so I am writing that as r square outside. So this will be dA you can write here, right? So then this value will be sigma is equal to 1 by r square into this area of the dA is nothing but we need to add such a small elemental area of the sphere there. Then you will get the complete area of the sphere. So complete area of the sphere means then we can write that complete area as 4 pi r square, right? Therefore this complete solid angle will be 4 pi steradians. So that means complete solid angle of the sphere will be 4 pi steradians. So here you should note that complete solid angle of any three-dimensional object will be 4 pi only will get. Not only for the sphere, it may be of any shape. It may be some irregular shape also. The complete solid angle will be 4 pi only will get. For the sphere, we can prove simply like this. Otherwise, if you are taking any such a irregular object, then some lengthy calculations will be included there, because theta value may vary and area of the different elements may vary, and so that some lengthy calculation will be there. The total calculation is not required for us. So let us conclude here. So the solid angle of the complete solid angle of any object will be 4 pi only. So mention that point there. The complete solid angle of any three-dimensional closed object will be three-dimensional, 3D. So the complete solid angle of this is steradian. So the complete solid angle of any three-dimensional closed object we can write as it is 4 pi steradian. It is not only for the sphere. Sphere we can prove easily like this. So it's actually for any object you will get 4 pi only. So that's an important point there. Now see the our required relation. That means our required relation regarding the solid angle here. Relation between solid angle and the semi-vertex angle of a cone. Relation between solid angle and semi-vertex angle of a cone. You know, vertex angle means, semi-vertex angle means it is like a two-dimensional angle. That means a plane angle and solid angle relation. In one way we can say like that. So now for this what I am taking is I am assuming a object, and this relation will be used in this optics lesson also. So when we are discussing the optics, I will explain this, that relation, that final relation. Right? Now this is a cone here of radius, base radius, suppose a small r I am taking here. Now this is a solid angle here you will get in three-dimensional. So that solid angle and the semi-vertex angle means, suppose I am taking this semi-vertex angle as theta. So we are going to write this relation between that solid angle and the semi-vertex angle here, right? So for that what we need to do is, we need to use our solid angle definition. So let us use the solid angle definition now. Solid angle is nothing but ratio of area of the element by the square of that radius we need to write. So now here we need to write the ratio of, that means the area of this element we need to write. Area of that element means it is like it is a part of a sphere above that cone. Above that cone means exactly, if I want to say, if you are taking like ball ice cream, if you are taking a ball ice cream, above that cap will be there, right? So that area we need to calculate here. Such a part we need to calculate here. Above the cone means above this cone you will get such a part of a sphere, spherical. So that area we need to calculate here. Got it? What area we are going to calculate? That area by square of this radius. That gives our solid angle here. So that gives our final relation between solid angle and the plane angle. So the area is clear. Just if you take a ball ice cream, so then for the ball ice cream cap will be there. So that area of the cap we are going to calculate here. That means that becomes area of the part of a sphere which is above this cone here. So for that let us see this calculation. I am drawing this part, some larger part here. So I will represent this cone as a just plane here. Just I am representing like this so that you can consider the small element easily. So actually it will be like this only. Just to take a small element and then for the integration I am taking that I am drawing this separately like this, right? And so now here I am taking a small element here. This angle is theta and this is d theta I am taking here. And so that area of this small circle will be smaller you will get. That means in that small cap we are taking a small element like this. So this element we are taking here. Got it? That element will be actually in 3-dimensional, that element will be in the form of a circular ring you will get. Total complete circle you will get. And so now here I am writing the area of a small element. So area of small element is equal to dA is equal to, so that I can write as 2 pi r into r d theta. So 2 pi r will give us circumference into r d theta. So this width, right? So this is dA is equal to, now small r value by using this triangle we can write that small r value as, where small r is equal to r sin theta we can write here, where this capital R is a radius. So this is our capital R here. So this small r we can write as r sin theta we can write here. And so then this will be r sin theta into r d theta. Therefore this dA is equal to, so 2 pi r square sin theta d theta, right? So that is the area of our element. So now we need to integrate that area of that element there. So now the total area we can write as integral of 2 pi r square into sin. So do one thing, here we are taking this as this complete angle we are taking as theta. Then do one thing, let us take these angles as phi and d phi here. So this angle I am taking as phi and d phi. So that finally the limits you can take from 0 to theta there. This is from phi to d phi. And so then this is from phi to d phi. And limits are now from 0 to theta we can consider. That means 0 means you will be here. And that theta means you will be here. That means from here to here in the reality. And so now let us integrate this expression now. 2 pi r square into integral of sin theta is nothing but you will get minus cos phi, and limits are from 0 to theta. And so its area we can write as 2 pi r square into 1 minus cos theta you will get, right? Now let us write the solid angle definition. Solid angle is equal to, this d omega is equal to a by r square, right? So therefore this d omega is equal to, r square will be cancelled, 2 pi into 1 minus cos phi you can write here. So sorry, cos theta. So that is the relation between solid angle and the plane angle. That means if the semi-vortex angle is theta, semi-vortex angle of a cone is theta, then corresponding solid angle we can write as 2 pi into 1 minus cos theta. It's an important relation. If you remember that relation, then we can solve some lengthy problems very easily. In a single step we can solve that. If you are using the integration, it will take nearly one page calculation will be there, one full page calculation. But whereas if you are using this formula, if you are using this relation between solid angle and the plane angle, so you can solve it in a single step. So regarding the solid angle now, you need to remember one basic definition like dA by r square is a solid angle, and for the complete solid angle of any object, any closed object will be equal to 4 pi, and this is the relation between solid angle and the semi-vortex angle we can write here. So that means theta is the semi-vortex angle of the cone. Then if theta is the semi-vortex angle of the cone, then angle subtended by the cone we can write as that 2 pi into 1 minus cos theta we can write. So that is the important relation you need to remember here. So now let us see one problem based on this. So now write this problem. A charge q, a point charge q is placed on the axis of a disk, is placed on the axis of a circular disk of radius r, axis of a circular disk of radius r at a distance r from its center, at a distance r from its center as shown. Then find flux passing through the disk. Find the flux passing through the disk. So in general, with the knowledge up to now, what we know, if you want to calculate this one, the general procedure what we can do is, we take a small element and then integration. That means, this is a complete disk for example, then here I am taking a small element. The general procedure I am explaining here. We take a small element like this, and due to this charge here, the field will be along this direction, the area vector will be along this direction, right? So this angle theta now we can consider it, right? And so now this angle theta we can consider here. And so now we take a small element, that means this distance is r and this is capital R. So this distance x if I cancel, then electric field expression is kq by x square. Kq by x square. So it will be kq by x square here. So when it is kq by x square, we can take this value as tested flux we can write as d phi is equal to E into the area of that element we need to write it as 2 pi r dr into cos theta. And then by substituting that value kq by x square into 2 pi r dr into cos theta. So cos theta also actually we need to write in terms of this r and this expression. Then cos theta also we can write that expression as like capital R by x. And finally by converting that x into in terms of r and x, we need to integrate that. That is the general procedure. If we don't know anything, any calculation, any formula or anything. So that's the general procedure. It's a very lengthy calculation. Now I am using this our plane angle and solid angle relation here, right? And so now for that, just I am taking this as, I am just joining these lines here. These are we are extending here these lines, so that it forms like a cone. And so now this angle I am taking as theta. So that theta we can define it as, suppose if I write the tan theta or cos theta, let us define from that. So cos theta is equal to, I can write this as 1 by, that means r by root 2r unit. So that is 1 by root 2 cos theta by, right? And so now here finally what we are going to write it is, this point charge will produce some flux here, right? That flux will be a part of a, that means that flux will be associated with this sphere if I consider here, like with this whatever the radius is there, with that radius if I imagine a sphere. So then the flux passing through that entire sphere will be Q by epsilon naught we can write. So in terms of solid angle if I want to answer, that flux will be passing through a solid angle of 4 pi, right? Because we are taking a complete sphere. So then flux passing through the entire sphere will be 4 pi, that means it is corresponds to a solid angle of 4 pi, we can say Q by epsilon naught. Flux will be associated with the solid angle of 4 pi. Now we need the flux passing through this amount of solid angle. We know this solid angle here, right? So then I can write this as flux passing through the passing through a closed through a sphere around charge is, means I will write here the charge is equal to 5, I am taking here 5 total. This will be equal to Q by epsilon naught we can write here. So just if you are able to derive one, we are going to derive another formula now. That formula now we can apply for any problem in such type of problems there. So right. So that means now if I imagine a sphere of radius is r, then here you will get like our previous a part here, a cap according to the cap we will get like this. So this will be a part of the cap actually like this. So if I imagine a sphere like this, then flux passing through that total sphere will be Q by epsilon naught we can write. That means now I can write as flux associated with the solid angle 4 pi is equal to Q by epsilon naught. Because it is a complete sphere, flux passing through the complete sphere, then I can say that this solid angle, this flux is associated with the solid angle of 4 pi, right? And so then flux per unit solid angle I am writing here. Flux per unit solid angle. So this I can write as this total flux by 4 pi. So which we can write as Q by 4 pi epsilon naught. Got it? This is the total flux. Just we are calculating flux per unit angle, unit solid angle. So we are dividing this total flux with 4 pi. So that is nothing but Q by 4 pi epsilon naught. Now we are going to calculate our flux associated with this solid angle here. This solid angle, for example, I am taking it as some d omega. This solid angle I am taking as some d omega here. Now flux passing through that solid angle we need to write here. Solid angle formed by given disk d omega is equal to, this is 2 pi into 1 minus cos theta. So this is the formula previously which we derived, the relation between solid angle and plane angle, right? That means if you are taking this disk as a base of the core, then solid angle is subtended by the disk at its center. That means at this point here, its vertex, that solid angle we are taking as d omega. And this relation I am directly writing here just the previous derivation of this part, right? And so now flux through the disk is equal to flux through the solid angle d omega. Got it? So we need to calculate actually flux through the disk. So that flux through the disk is nothing but equal to the flux through the solid angle. And so that I can write this as flux through the disk, we can write as this flux per unit angle, unit solid angle, 4 pi epsilon naught into d omega we need to write. Like our linear charge density or aerial charge density, for example, for taking. So linear aerial charge density means charge per unit area into area of the small element we are writing here. So similarly this is in terms of solid angle we are writing here. In terms of solid angle means charge per unit unit solid angle into the required solid angle. So then we can substitute this value there. So I can write this as 4 pi epsilon naught into 2 pi into 1 minus cos theta. Therefore, so it is q by 2 epsilon naught into 1 minus cos theta. So it's an important formula now. You need to remember this important formula here. So whenever such a type of problems are there, now directly you can apply this formula. So there is no need of remembering any this calculation or integration that is not required. Just we can apply directly this formula here. So that means there, when the charge is placed at this point here, now we are calculating the flux path into this circular ring or circular disk. We can consider q by 2 epsilon naught into, so that is q by 2 epsilon naught into 1 minus cos theta we can write, right? So that now for the cos theta value we can calculate by using this diagram. So in this given problem, that value we can write as 1 by root 2. So we can substitute that value here. So this formula is very important formula. You need to remember this formula here. So flux passing in such a case, q by 2 epsilon naught into 1 minus cos theta. In many problems we use it. Such as similar to this, many problems will be there. So we can use that formula now. So in this finally we can write in this calculation here. So finally we can write here this flux will be equal to, in this given problem, this is, so q by 2 epsilon naught into 1 minus 1 by root 2 we can write here. Got it? So it is the final answer for this question here. So this is the formula here we need to remember. Once again I am saying that this is an important formula. So q by 2 epsilon naught into 1 minus cos theta, that is the flux passing through the base of base of the pole we can say, or you can say this is circular disk. That means the same question, instead of this disk they may ask like this. A charge is placed at this vertex of this cone here. Then what is the flux passing through this cone? What is the flux passing through the cone is nothing but our given this problem only. You can answer this q by 2 epsilon naught into 1 minus cos theta, where the theta is nothing but this angle, half vertex angle or semi vertex angle. So that means the question they may ask like this. Now here I am explaining simply this question now. So on this axis of the disk here, I am placing it two identical charges at the same distance, say r and r. Then what is the net flux passing through this? Net flux passing through this disk here. So here simply you can answer that net flux passing through the disk 0. Can you say reason? The flux due to this charge is given by that expression. You can write it as q by 2 epsilon naught into 1 minus cos theta. You can write that flux will be along this direction, right? Because this is a positive charge, away from the positive charge, so towards right you will get it. And now flux due to this charge will be given by the same amount because the distance is same, and so then this flux will be along this direction. So if one is taken as positive, then other will become negative, right? So that the net flux will be 0 you will get. So in this case the net flux will be 0. Now for example I am taking the situation like, so on one charge is negative I am taking here. the same disk question, this charge is plus q, which is at a distance of r from the center, and this side minus q will be there. This is a disk of radius r. Then net flux passing through the disk we need to write. So now here simply with this knowledge you can directly say that the flux passing through this positive charge and here positive charge, they are cancelling with each other because their flux will be opposite in direction. But here the flux due to this positive charge will be from, we can say, from left to right, and flux due to this negative charge will be from right to that is also towards from left to right, because it is a negative charge. Negative charge in the sense the electric field lines will be towards the charge, so it is also crossing from left to right only, and so both the flux are in same direction in the right here. So this net flux will be equal to flux due to the positive charge plus flux due to the negative charge, and so we can write this as this capital Q by 2 epsilon naught into 1 minus cos theta plus Q by 2 epsilon naught into 1 minus cos theta. That means you can just multiply with 2 here. So Q by epsilon naught into 1 minus cos theta we can write. So if for example in this case the theta is given like this, 45 degrees you get here. So I can write this as Q by epsilon naught into 1 minus 1 by root 2. So that will be the answer for this question. So if both are positive charges, net flux will be 0. If one is positive and other is negative, just we should multiply with the 2 because their flux will be added together. Now here for example I will give another problem based on this. So let us try to solve the question. So this is cylindrical surface here. So we are placing this a charge Q at the center. A charge point charge P is placed at the center of this cylindrical surface. This radius of this base of the cylinder is r, and length is, let us take it as 2r, total length. So that this is r and this is also r. Right? Means write that problem. A point charge Q is placed at the center of a cylindrical surface. Cylinder at the center of a cylinder of radius r and length 2r. Then find flux passing through the each plane surface, flux passing through the each plane surface of cylinder and curved surface of the cylinder, So try to solve that problem, otherwise I will explain in the next class. So similar, we can apply this formula. That formula that Q by 2 epsilon naught into 1 minus cos theta, we can apply that. So try that question, otherwise I will explain in the next class.